Now this is a Commodore SuperPET SP9000. The concept was designed at the University of Waterloo to teach programming, adding a board containing a Motorola 6809 CPU, 64K of additional RAM, and an RS-232 serial port. It then offered a suite of programming languages designed by the university, including BASIC, APL, COBOL, Fortran, Pascal, and a 6809 assembler. Commodore shipped it in the late fall of 1982 for $1,695 in the US. It was the last in the series of the original PETs, offering everything they provided, along with the programming bundle and terminal software. The idea was that students, professors, or developers could write software locally at their machines and then interact with and send completed projects to a larger mainframe. Commodore, naturally, didn't know how to market the machine, but it didn't end production until 1985. The only known sales figures are from summer of 1982, when Commodore claimed 6,444 SuperPETs were sold. So since we're stuck with it not booting, let's get this thing taken apart. The daughter board sits on top of the 8032, and it's connected with a ribbon cable that reaches from where the 6502 goes on the original motherboard up to the daughter board where both the 6502 and 6809 reside. The daughter board is a lot flimsier than the 8032 board, but it is well laid out. To make it work like an original PET 8032, you just pop that 6502 back into place.
Pin 2 is 5 volts. As it starts.
Checking levels showed that we had address lines, that we have a clock,
Interrupt is high.
but select activity is nil.
Non-maskable interrupt is high.
Now, just to verify I'm not crazy, I wanted to check the chip select lines. So tracing back from the ROMs are these 74 chips that control the chip select. So checking that on this really quick to see if there's anything happening. And, well, it is. Alright, it's been a bit. Hopefully, where I last left off, all the video stuff was removed. Looking at the ROMs, there isn't anything obvious. I swapped out the CPU with a Rockwell CPU just to see if that would change anything, and it didn't. What's next? I am going to put back the original CPU, but what I have done in the meantime, I have this new handy dandy toy. This guy right here is a ROMulator by Bitfixer. I just put this together today. Hey, look at that. ROMulator. Down here is the actual ROMulator itself. I will be putting the 6502 right here. Here's the controller for it. And here is the programmer for it. What I'm going to do is I'm going to remove the old one. I am going to take my original 6502. I am going to put it in here. My fake notch. 6502's in. Put the ROMulator in its place. On the video pin, let's see if we see what we're supposed to see. Oh my god! It made the noise. I'm seeing video here on the oscilloscope. Can I get to the ROMulator? I sure can. Yeah, it actually works. So the 6502 is just fine. The downside here is that now I have to figure out how to use this thing to maybe selectively remove ROMs, if I can. And I don't know if I can, but just to verify, put our video stuff back in place. Let's see if I also have a monitor to repair. There's a display. It works. How's this keyboard? Honestly, better than I thought. I was gonna have to clean this anyway, but the keyboard works. That's fantastic. So now, a little bit of research to do. I'll be back when I do. I went to GitHub to take a look at the ROMulator Git repository to figure out how to configure the ROMulator to give me access to only certain ROMs or certain memory spaces. There is a lot here in this repository. This is very, very, very cool, but a little complex. So I have grabbed the repository locally. If you know VS Code, these two are green because I have done the full build and I've grabbed all the ROM sets and built all the tests. And with those, now I can actually build a full firmware image that I can send to the ROMulator. And I tried that out and that worked. So now what I'm going to do live is try to get access to just some of the ROMs. So if we pop over here to the documentation, there's this config section. And the ROMulator configuration is made up of memory maps and memory tables. So the example they have here is for the PET 4032. And basically what this is saying is this memory map is made up of indexes. The indexes that they provide you are 0 through 15, I think. They represent binary from the dip switches on the ROMulator. So when you set a dip switch, it's just a binary encoder effectively, and you're setting an index number for which memory map to load. So in this case, it is loading up 3 basic ROMs, an edit ROM and a kernel ROM into their memory spaces. Now, if you go down to the enable tables here, this is similar where it is setting the index, your start address, your end address, and then how it should treat that memory space. So by default, the ROMulator is going to take over everything. It is going to replace your RAM. It is going to replace all of your ROMs, and it does that via these keywords. Read write is for your RAM, so you can read or write to those memory addresses. Read only is for ROMs, and pass through ignores the ROMulator and goes directly to the original space. So it'll be your original RAM or your original ROMs or so on. By default, it's going to do all of that. So if I go to config here and memory set default, right? What I was using was index 2, and 2 because the SuperPET is effectively an 8032 with the additional daughter board. So when I remove the daughter board, I effectively have an 8032. So I've got my 3 basic ROMs, my edit ROM, my kernel. Now, I'm going to split this over and I am going to do my enable table over here. So the enable table says that for every single one of these indexes, it is setting this space to read write, this space to write through, this space to pass through, this space to read only, pass through, read only. And then your exceptions are below. So it reads this like a CSV file, and then anything that matches a previous entry, it replaces. So you'll note up here, 8000 through 8FFF is write through, but then down here, 8000 through 83FF is VRAM, and it's defining a ROM, right? And then E800 through EFFF becomes write through. Same down here, exact same down here. So in theory, if I wanted to open up a space, I would basically turn everything to pass through. That's kind of what I'm gathering here. So if I go down here, I'm going to keep my index 2. I'm pasting this in, and we're going to have this just be an exception for index 2. And that sets it to pass through. So theoretically, with this configuration at index 2, I am sending everything to the original chips on the board. Since it did work before, I am guessing this is not going to work because I do think there's a problem on the board and not with the socket or anything. So in theory, when I boot up this machine with this new configuration, it should fail. So to program this, what I'm going to need to do is provide some power, which I should probably find. You can turn on the machine to provide power, or you can connect it directly through USB, which is what I'm going to do. Beware, this does seem to send power through to the board because it's connected to the CPU socket, so I don't know if that'll actually affect anything. All right, we have a solid blue light. We actually need to compile this. Opening up a terminal here, we go make ROMulator, and it's going to build us a ROM. While we're doing that, I'm going to go to the web interface. And so the ROMulator is responding. And I'm probably going to speed this up here. So it grabbed all the ROMs. It built a binary file. It is stored here in bin romulator.bin. Come on over here. I will browse to the firmware. I'm already there because I'm already there. And program. I will probably speed this up again. Throughout that whole thing, all we got was one red little flash that said it was done. So I can pull the power now. I'm going to guess there's not going to be a chime. If there is a chime, then I've got a socket problem, in theory. So the ROMulator got power, no chirp, no chime. Just for fun, I'm going to read the VRAM, which I think is going to be blank because I don't think it can read the VRAM. Yeah, it's nothing. It's nulls. So because it didn't replace the VRAM, it can't read the VRAM. Okay. Now, to double check that this actually worked, what should we enable? 000 to 7FFF is the internal memory. So if you look over here, we got B000, C000, D, E, F. This is all pass through. It's all pass through. This right here is basically the ROM set at play here through FFFF because that matches over here, that kernel ROM, right? So everything else, I don't know what these are. Why don't we pass through all the ROMs and let's keep the RAM and let's have the ROMulator do the ROMs. So passing through the RAM, keeping the ROMs on the ROMulator. Do we get a chime? No. No, we don't. All right, so that was a big block of stuff that we changed, but it effectively meant that we passed through the RAM and we kept the ROMs on the ROMulator. Just for fun, I'm going to do the opposite. Comment this out because I'd like, that's commented out, everything else is passed through. Now the RAM is staying on the ROMulator. Okay, moment of truth. Do we get a chime? Well, my friend. Roll camera to just show. SuperPET. Prompt. So what does that mean? That means our problem is with our RAM. That doesn't mean it's the actual RAM chips that are bad, though it very well could. And it could be a logic chip that is preventing RAM access to work properly. So my next step is going to be probably to remove the ROMulator again from the equation. Or first step is going to be to set everything back to pass through while this thing is up and running, just to keep this on the board instead of taking it off. And then I'm going to start checking signal levels, and then maybe I can open up individual address spaces. But that seems like a good place to start the next video. So I will see you in the next one.